Okay, so yes, Erlang, concurrency, and LFE. So what I had a thing, I'm not really sure what people know and don't know, so what I plan to go is basically describe Erlang, the ideas behind it, the concurrency model, but when we get to the sequential language, I will then use LFE to describe that instead. Okay, so we'll get a bit of both, hopefully. And if you find you know all this, just shout and I'll go very fast through it. Otherwise, if you have questions, please ask them. Let's see how this works. Does it work? Yes. So, a little bit of history, not too much, I promise. A bit of philosophy, a bit about the Erlang way, concurrency, error handling, and then we'll get on to LFE towards the end. And when you feel you've had enough, tell me. Right. So, history. So, this is now we're getting back to early mid-80s. Right? This is how far back it is now. And Ericsson had then a very good product called the AXE telephone exchanges. And they were a very successful product. They made Ericsson a ton of money, and they were very successful, and they sold a lot of them over many years. And they're actually still in existence in the mobile base stations, mobile switches. Now they're all emulated, but before it was all hardware and specialized software and everything like this. And it was very successful, was costly and difficult to maintain. So there was an computer science lab at Ericsson, and one of the things they were looking at, how can you simplify developing and maintenance of these type of things, these type of applications, right? That, by the way, is a real picture. That's not fake. This is back in the old days when all the telephones went through cables. Right? So if you had an exchange with a few 100,000 connections to it, you could have a few 100,000 of these wires coming in, and they actually look like that. It's quite fantastic. It actually worked, to be honest. So, by the way, can you hear me?
Yeah.
Right, great, thanks. So that was one of the things the lab was supposed to look at. How can we improve developing and maintaining these type of systems? And we did a large number of experiments on this. So what we had a small business exchange with four telephones connected to it, which we had connected to our VAX. We had a VAX Unix. We had the first Unix machine in Ericsson, actually. And we could control the telephone exchange from the VAX. So we did a lot of experiments on how you would program these systems. And basically, we tried with everything we could run on our Unix machine. We must have done about 30 or 40 different tests on these type of things. Some very small, trivial ones, some quite large and complete. So, for example, one guy did an ADA version, and that was quite good. It had a lot of functionality in that. The main difficulty was trying to get asynchronous communication through Rendezvous. That was the main difficulty for it, which you had to have. So we did a lot of these experiments. And one of the things we found was that basically, in our opinion, none of the existing languages and systems were actually very good at this. And that gets back to the problem domain. I mean, what type of problem is this? And if you look at some of the properties of the problem, it's there's a lot of concurrency in the system, in the problem, in the solution, in the system. So I mean, if you have an exchange with a few 100,000 connections, you might have tens of thousands of calls going on at the same time, plus everything the switch has to do while it's running. So there's a lot of concurrency inherent in the problem itself. They have to be fault tolerant. The switch must not crash, right? That's just not an option. We have a lot of timing constraints. I mean, classic, you lift the receiver, you get a dial tone, it has to come within a certain time. Irrespective of what the system is doing, that should happen. Right? So that's a very basic one, but there are a lot of timing constraints in the system. You just had to be able to obey. Continuous operation for a long time, yes, you could not take it down. You're not supposed to take it down to do things, even like upgrades and stuff like this. Continuous maintenance, evolution, the same thing. Distribution. Again, these were fault tolerant. And if you want to build a truly fault tolerant system, you need at least 2 computers. You cannot do it on one computer. You need at least 2 computers, which means you need some form of distribution so they can talk with each other and coexist properly. So these were things that we found were inherent in the type of problem we're trying to solve. So yeah, A few reflections afterwards. Thing is, we actually were not out. We're not out to implement a functional language. We're actually not out to implement a language at all originally. So it was Joe Armstrong who started. He says, I'm number 2. There was the third guy, Mike Williams, and we were the 3 in the core at the beginning. And we had a set of rules for telephony, and we're trying to implement these rules. And then you find, well, if you have rules, of course, if you can make one connection, you want to make many connections. So you have to attack the problems of concurrency. You have to attack the fault tolerance. You have to attack the fact that a lot of other things going on in the switch as well. So you end up with a functional language, or end up implementing a programming language. We were not trying to implement a functional language. That just happened, right? Someone told us after a while, you've implemented a functional language, and we sort of said, oh, right, good. I don't know if you can see that both ways. You can see that as a very good sort of proof of the benefits of having functional programming. Right? We're not out trying to implement the actor model. Okay. Again, this is something we arrived at our solution because we felt this was the best way of doing things. And someone told us later that we'd implemented the actor model. We'd read about someone saying Erlang implements the actor model. So then we went out and tried to find descriptions of the actor model, because we'd never heard of the actor model, to be honest. And then we found that and said, yeah, we do have done that, right? But this wasn't the goal. This is where we arrived at. We were trying to solve the problem. This was our goal, right? We had the problem. How do we solve the problem? We didn't, in a sense, we didn't care how the actual details, just as long as the solution worked, right? There's some more things here. That made the development of the language in the system very focused. So we were trying to implement the systems, and to do this, we found we needed a better language to do this. So the language and the system evolved at the same time, right? That meant we had a clear set of criteria what should go into the language and what the system should be able to do and what the system had to be able to do. If we came up with a fantastic idea, then the thing was it useful? I mean, you have a lot of good ideas, but was it actually useful for what we were trying to do? And did it or did it not help to build systems? And sometimes we came up with great ideas that just weren't any help, that just weren't useful, and we just got rid of them. And this made the whole thing very tight, because we had a clear goal, right? Good, bad. If it's good, we keep it. If it's bad, we get rid of it, which meant things didn't grow. And the language and the system evolved to solve the problem. So the language and our way of working with the language to build a system evolved at the same time. So the features that went into the Erlang language went in because we could use those to build a system we thought was very good for solving that type of problem. So it sort of worked both ways, right? And seriously, we came up with a number of, we thought, fantastic ideas. We were very lucky to have a user group who could test our stuff. They were looking at doing an architecture study for small exchanges. They wanted a language to prototype their architectures in. So they were using Erlang to prototype their architectures, and we could get very good feedback from them of which ideas were good and which ideas were bad, both at the language level and our ideas of how you build these systems, right? So we came up with a number of things we thought would be fantastic to help their solutions, and they just said, no, it's great, but we can't use it anyway. So yeah, so that was a very clear focus for it. And if you look in the Erlang language and look in the system, it is very focused. There's not much extra junk in there, right? Which often happens. So yeah, so where do we end up with all this? Well, the first principles, lightweight concurrency. What we arrived at was that concurrency was such a fundamental part of the problem, you had to build support for this in at the bottom. It's not something you could add as a library on top of it. It was just too fundamental like that to do that. It was almost at the same level as doing a function call. It's just, this is what the system was doing all the time. I've got a very short code example towards the end. So you have to have a large number of processes, has to be fast. We need asynchronous communication. The system must never block. Blocking is just not allowed. And if you ever try to write non-blocking systems with synchronous communications, you will find that is very difficult. If you look at the the end of the code mesh talk I gave 3 days ago, 2 days ago, 3 days ago, I give an example of what happens when you try to do asynchronous communication where you shouldn't, right? And the whole system blocks in about 5 seconds, and very well. Process isolation, this gets back to how we handle errors. If things go wrong, processes should crash and you should not be able to destroy things for other processes. We need support for error handling. This is the same thing, same idea as with the concurrency. The error handling is so fundamental, you need to build in the basis for it in the system itself, at the lowest level. It's not something you can add at the top level. Continuous evolution of the system, yes, we need software upgrades. We wanted a high-level language. Okay. However you look, Erlang's reasonably high level, not super high level today, but reasonably high level. We also had the idea that the language in the system should be simple. There should be simple in the sense that there's a small number of basic principles. But if you get these principles right, then you can build complex systems on top of that. You don't want a complex base, because that makes everything complex. So in this case, simple is good. If you get them right, then you can build complexity on top of it, but the basis is simple. That's difficult, by the way. Complexity is easy, right? Simplicity is difficult. Building complex systems is easy. Just pour in more stuff and it gets complex, right? That's easy, right? Anyone can do. Making things simple is difficult. That takes time. And the language should be simple to understand and program easily. And what we found, as I was saying with our experience, we don't provide solutions. We tried to do that and we usually got them wrong. What usually happened was we misunderstood the problem. So we came up with a very good solution to what we thought was the problem, then we give it out to our users and say, yeah, that's not the problem. So we got around to provide tools for it. Provide the basic tools for it, let the users build the solutions they need. And that, yes, that works. So there's some first principles of it, basic for it. So we'll go. So I would normally talk sequential here, but we'll push sequential till later. Actually, I hope this works. So Mike Williams, the third guy in the group here, he was actually the one who knew most about telephony because he'd worked for I think 10 years for Ericsson before that. And he said, well, the concurrency, 3 properties of a programming language that are important is the time to create a process, the time to perform context switches between processes, and the time to copy messages or communicate between processes. These are fundamental things. If you want a fast concurrent system, these things have to be fast. If they're not, then you will not get a fast concurrent system. That sort of, in a sense, rules out typical operating system processes and operating system threads, because they are big and they're heavy, they take a long time to create, the long time to do context switching and things like this for it. And you can't get enough of them anyway, right? So if you want to build a truly concurrent system, these are 3 things you have to be able to do very efficiently. And yeah, how do we do it? Well, we actually managed to get it very simple, truly. There are 3 basic principles that underlie the whole concurrent Erlang concurrency model. We have lightweight isolated processes. They are truly lightweight. You can run millions of Erlang processes on one machine. The current implementation sets the limit at 134 million. Okay. I have never seen anyone run that many. You tend to run out of memory before that. Ulf Wieger did 20, he got up to 20 million. He was just creating processes. The largest number I know of in production systems is, of course, WhatsApp, and they were doing 2 or 3 million processes in their system. Yes, but they had one. They were. Yeah, they were running. They came out and said they were running 2 million concurrent TCP connections on one machine on one Erlang system, and there's at least 1 Erlang process per connection. So yes, you can do it, and it works. I don't know if that's a good way of doing it, but that's another issue, but that works, right? Well, getting back to fault tolerance, if the machine crashes, you're suddenly losing an enormous number of connections, right? In that sense, it's probably better to have multiple machines, so you're more fault tolerant. Asynchronous message passing. Again, that's the base. If you base things on synchronous message passing, it is extremely easy or extremely difficult not to block things. And once you block, all your timing constraints go away, right? So blocking was just not an option. And we have a selective receive mechanism. So when you're sending messages to a process, the process receiving the message can can decide when it wants to handle that message and which messages it wants to handle. So you avoid a combinatorial explosion. You don't have to handle every message everywhere. I can say, I'm just interested in this message, and I'll ignore the other ones for the time being. And they are the three basic principles on which the whole concurrency model is built. And when you want other things, you build them on top of that. So if you want synchronous communication, well, you send a message to the other process, and then you sit and wait for it to reply. That's how you do synchronous. That makes things much easier, because I can be very specific on how I want to make my synchronous communication. And often you will want you want your communication to have different properties in different applications and even in different parts of the same application. So yeah, so these are the ideas. A bit about processes. Okay, so everything is run in a process. So there's nothing outside the processes. Everything is run in processes. All processes are equal. Erlang is a very egalitarian system. All processes are equal. There are no special or system processes. They're just processes. There is no process hierarchy. Process space is completely flat. So, yes. And we use processes for many things. We use processes, well, for everything. For concurrency, of course. How do you manage state? Well, you have processes that manage state. So we do processes for everything. Communication. The only way to communicate between processes is by sending messages. That's it. And all message sending is asynchronous. I send a message, send and pray. I send the message and I keep on going and hopefully it arrives at the other end and it does something. Yeah, the built-in functions, BIFs stand for built-in functions, and they're all asynchronous as well. And it actually works almost exactly the same with distribution. I can send a message to a process whether it's on my node or another node, more or less the same thing. So yes. There is a concept called ports. This is how we talk with the outside world. This is one of the two ways of talking with the outside world. From the Erlang point of view, the outside world looks like a process. So I send messages to the outside world, and the outside world communicates with me by sending messages into me. Right? And the outside world can be, well, it can be your screen, or it can be a telephone switch, or it can be another machine, it can be anything. Or bits of hardware, it can be a database, whatever it might be. Right? And yeah, so the outside world looks like a process, so we send messages to it. It works the same way for the error handling mechanisms we'll see and things like this for it. And we can use Erlang ports to talk to anything. So Erlang was reactive from the very beginning. We were buzzword compliant 25 years ago, right? So we're reactive and we're asynchronous, we're functional, we're whatever you care to choose, we are it. Right? And we always have been it. And again, we didn't do it this way because we wanted to follow these to be buzzword compliant, but this was the best way we found of building these type of systems. So I can't stress how difficult it is to build truly non-blocking concurrent systems if you don't have asynchronous communication. It's a challenge to do that. Yeah, that's me at work. So actually, that thing here, that is a small exchange. That's the small exchange we were experimenting with. So we could plug 4 telephones into that and we could actually call things. And working with real hardware is an experience, right? Because it doesn't always behave as you think it should behave. So yeah, this was for a trade show we were doing about 90 or 91, and we wanted to demonstrate Erlang. And having that box there was pretty useless because they're not very impressive, no blinking lights or anything like this. So we said, we'll do a train set, control that with Erlang. And I think I went slightly overboard. Okay. Well, we had a system, relatively complex track with blocking and things like this. We're running 2 trains. I designed an ATC system to control everything so the trains wouldn't crash, and we had a lot of fun. I just implemented what you call today a DSL, how you could program these things up so you have a long sequence of things what the train's supposed to do. A colleague of mine did a graphical interface so you could see on the board where the trains were and everything was going on like this. It was a lot of fun. And it worked. For 1 week, a whole week for a trade show it ran. But yes, so we could do other things in Erlang as well. So that's basis of the concurrency. It is very simple. And it doesn't have to be more complex at the base level. So error handling. The basic principle here is, the basic idea is, errors will always occur. Okay, just accept it. No matter how good or bad your system is, you will always get errors. Software errors, hardware errors, whatever, you will always get errors. Okay. That's rule number one, you might say. And rule number two is the system must never go down. These were requirements we had. Yes, errors will occur. The system must not crash. So parts of it might go down. We can accept that. If we're talking telecoms, yes, we might lose an occasional call or connection. That's okay, right? It's not good, but it's not bad. Just as long as the system must never go down. The switch must not crash. The switch must be able to handle these errors and keep on going, right? And this was, again, same thing. If we couldn't, same thing with the concurrency. If we couldn't make a truly concurrent system that could handle the level of concurrency we were after, any solution we came up with wasn't interesting. If we could not build fault-tolerant systems, whatever solution we came up with was not interesting because we just had to do it, right? So the system, you have to be able to detect, contain, handle, and recover from errors. They're going to occur. Accept it and get over it and work with it. What we want, so robust systems must always be aware of errors. But we want to avoid writing error-checking code everywhere. If you've ever done that, it's a real pain, right? You have to check error everywhere to do it. If you miss it or get it wrong somewhere, you can be absolutely certain that's going to kill your system, however it is. We don't want to do that. We want to be able to handle processes crashing among cooperating processes. So typically we have a number of processes working together doing something. If one of them crashes, the others have to be able to manage that in a good way, right? And we want to interact well with the process communication. So what we want to do, we just want to let things crash. That's the whole base of the Erlang let it crash philosophy. If something goes wrong in a process, crash the process and let someone else clean up after you. Okay. And strange enough, it works. So that was our goal, to do that. And of course, you have to design your system to be able to do that. So the error handling mechanism, well, it's process-based. Yes, if something goes wrong in a process, you crash it. If process crashes, then all cooperating processes should crash as well. The rationale being that if they're all working together and something goes wrong in one of them, you might as well take the whole lot down. The whole lot doing one thing, not the whole system, of course. And you need to be able to monitor them, of course. I have to be able to detect that they've gone down so I can clean up after them and do the right thing after they've died, right? You do sometimes need to handle errors locally. Sometimes it's reasonable to do that. There's a try-catch mechanism in the language. So how do we do it? Three basic principles again. We have a concept of links between processes. So you can link processes together. It's got nothing to do with communication. It's just I link to you, you're linked, a whole set of linked processes. And when a process dies or crashes, it sends signals along all the links, its links. And the process at the other end will crash as well. And it will send signals across its links. So if you have a set of linked processes together, one of them crashes, they all crash, which is great, which is exactly what we wanted. They all go down, right? However, how do I monitor them? So if I link to them, then I will die, which is not quite what I want. So we have something we call trapping exits. So I'm still linking to them, but when I receive the exit signal, I won't die, but I'll see it as a message instead in my message queue, which I can receive and handle as normal other messages to it. So I can sit and monitor other processes by linking to them, trapping exits, and seeing when they die by getting messages and handle that. And they're the three basic mechanisms behind the error handling. And yes, and strange enough, it works, right? So how do you use this? How do you build robust systems? We had these three basic ideas, but how do you actually use them? And at least two things you need to do if you're going to build a truly robust system. Some functionality must always be available. You will have a set of services that have to be accessible, have to be there for the system to be able to say the system is running. If I can't do that, it's not running, right? And you have to clean up when things die. When a process dies, it might have allocated resource or something like this. You have to be able to clean up after it, right? So it can die quite happily. And you need at least two machines again. So how do you do this? Well, we use signals and trapping exits for both of them. So for handling things, making systems robust and making sure that functionality is always there or service always available, we have something we call a supervision tree. So we basically split processes into two different classes. Again, this is the code that does it, nothing inherent in the process. And we have supervisors and we have workers. And we build what we call supervision trees. And workers do all the work, and they have a supervisor which just keeps track of them. So in this case, this supervisor, the grey process here, is supervising these three workers, and if they die, this supervisor knows what to do. Do I restart it? Do I ignore it? Maybe it just doesn't matter. Maybe perhaps I kill them all off and restart them all, because I know they're all working together to do that. So that's what the supervisor's job is, just to make sure that things that should be there are always there. So if I have a surface that needs to be available and that process or processes crash, its supervisor will restart it. So it'll be there. This supervisor, of course, this one supervises that supervisor and that worker knows about these things. So that's how you make sure that things are always available. That are there should be there. Right? We don't stop them from crashing. We clean up after they crash and keep on going. The other thing is, okay, how do I clean up after a process? I'm a service. I'm a server. I provided a service, and the process has allocated something from me, and it crashes before it deallocates it. How do I handle that? I can't leave it, because then I'll just run out of things. I can link to it. And when it crashes, I can link, and I can trap exits. And when it crashes, I'll get an exit signal, which converts to a message. I can receive that, and I can say, now that process has died, and I can clean up after that process and reclaim things, whatever I need to do. And yeah, that's basically how it works. That, strangely enough, it works. Right? I mean, if you hear Erlang getting 5 or 7 or 9 nines of reliability, that's how it's done, truly for it. And in that sense, we succeeded, because we managed to get a very core set of basic principles with which you can build things on top of it. So we were using links and exit signals to build supervision trees, because we could use supervision trees to give us that functionality of making sure service is always available. And yes. So a bit about modules and code. We'll see a bit more about this later. The system only has compiled code. Okay, that's it. There is no built-in interpreter. You just have compiled code. And everything's in modules, and the module is the unit of code handling. You compile modules, you load modules, you delete modules, you update modules. Everything is run through modules. I cannot have functions outside modules. We can have multiple versions of modules in the system at the same time. So I can upgrade the system by loading in a new version of a module and then going over from the old version to the new version while the system's running. It's not always easy, but the basic facility for doing that is there. And all functions belong to a module. This handling of modules also means there is no intermodule dependencies at all, because a module can just come and go when the system is running. So in one sense, the Erlang has no concept of a system. It has a collection of modules when it's running. When you build it, that's another thing. But there are no intermodule dependencies. So when I compile a module, I can assume perhaps at compile time certain things exist, but at runtime there are no guarantees that it actually do that. But this allows us to upgrade modules and upgrade the system on the fly, because I can just upgrade a new module with new functionality and just kick out the old one and do that and upgrade the system as it goes. So it actually works. OTP, Open Telecom Platform. What is it? This is what almost everyone uses to build systems, so it's nothing strange. I don't know, how are we doing for time? I have no idea. Am I going too fast, too slow? Please, I have no idea how long I've been going. Sorry. I've been going 30 minutes, right? Okay, that's not too bad, not too bad. If I'm going too fast, tell me. If I'm going too slow, tell me. Seriously, please. So yeah, what's OTP? The Open Telecom Platform. It's a set of design patterns for building concurrent fault-tolerant systems, right? So Erlang provides these basic tools. How do I actually use them to build a fault-tolerant system? We saw a bit about the supervision trees and stuff like that, and that works, yes. But how do I actually do it? And using a set of patterns to do it to help me to do it. So it's a set of these design patterns for building these things. It's a set of generic behaviors. That's the code that helps you implement these patterns, right? So a very typical pattern is the gen server, the client server pattern, and there is code that helps you implement that client server pattern for it. It's in one of the behaviors. And OTP provides 5 basic behaviors, but it also, it's easy to extend it to add new behaviors. So if I've got something that doesn't fit these 5, I can implement a new behavior, and if I do it the right way, I can fit it into the whole OTP system, and everything works. Right? This is actually not strange because all of OTP is implemented in Erlang. So all the libraries you need that OTP uses to implement its behaviors are there for you to use if you want them, or when you want them. It's a large set of libraries, actually. Sometimes people complain that there aren't many libraries. Yes, there are an awful lot of libraries. The difficulty is finding them. Well, they're all there, but finding out about their existence, that's a bit difficult. And that is one of the bad sides of the Erlang documentation. So we're on that. People complain about the Erlang documentation, saying there is no documentation. Yes, there's an awful lot of documentation. Everything's documented. But it has 2 problems. Well, depending how you view things. It's written in a reference manual style. So if you know what you want, you can go and find it. You can find definitions of the modules, the functions, what the inputs and outputs and what they do and everything like that. But it's not very good as a tutorial. So even the user guide sections, they will help you write things if you know what you want to write. But if you want to say, how do I implement this? No. Okay. So that's the problem with the documentation. And that gets back to the libraries as well. That's why people don't find all the libraries that are there, many of them. And there's a lot of support tools for building systems. So yes, I've got design patterns, I've got support for design patterns, but I also need support for actually using this to build a system. How do I put everything together to make a package that does what I want to do? Right? And there's a lot of support tools for doing that as well too. There are quite a few a number of common external tools now that are used for helping you do that.
Isn't there a big book being written about this?
Is there? You're writing a book partially about that, yes. Yes, there are books about this as well too. And there's a new one coming from Francesco. Soon. I don't know when, but soon. Soon. We'll leave it as soon, yes. Yes. There's support. There are tools. I mean, a very common tool in use for this is one called Rebar, for example. And then there happen to be 2 different versions of Rebar. But, pick Rebar 3 if you've got the choice because it's better. But yes. There are other tools as well for it, and the tools are part of the system. And there's the design, part of the design patterns in OTP is how you put things together to make a system, how you do these type of things. So here you've got information what goes into the system, how do I start the system, how do I stop the system, etc. like this, all these and things for it. And the external tools actually use the ones inside to do these things. The thing to remember is, even because of its name, there is absolutely nothing about telecoms in OTP. If you look at all the OTP libraries, there are no telecom libraries there. The closest you can get, I think, is an ASN.1 compiler, because ASN1 is used, amongst other things, in telecoms for protocols. That's about the closest. There's absolutely nothing about telecoms in there. So it's a very politically correct name to come from a telecoms company. There's nothing in it. So yeah, don't be scared off by the fact that it says telecoms. If you look in the documentation, I think it says Open Telecom Platform once or twice in the whole documentation package, which is about that thick, right? It says OTP everywhere else. So don't be scared off by the fact that it says telecoms there. It's nothing to do with telecoms. That's a little bit of general about OTP, for what it's all about. And I'm not going to go into it, but it's a big package of things. And all the thing with the behaviors, for example, they all work together. So if I use a supervisor behavior to build supervision trees, and then I use a gen server behavior to build client-server workers, I can put them into the supervision trees because they know about each other. They can talk with each other. They understand each other. They all work together. And I can use these things and stuff as well too. So it's a benefit of them. Yeah, so a bit about systems. When you start looking at Erlang systems, the structure of them tends to be very operating system-like. I mean, when you start up an normal operating system, you'll start up a number of processes, and there'll be processes for doing things, right? And if I want a shell, I'll pop up a shell process, and I'll get a window and do that. And if I want another shell, I'll pop up another shell process, and I'll do that. And what you find is, well, they provide service. There's very seldom a central thread of execution in an operating system. There's a lot of services, and I can run up lots of things in these, accessing these services. I mean, there's not one shell. There is one of how many shells ever I want, together with other things I'm doing, together with other servers, whatever I might be running for. And that's typically what you find in Erlang systems as well. There's very seldom a central thread of execution. It's not like I'm running one thing and starting up a few things in parallel as I go. I start up a large number of services, and then I can set up separate tasks for it. Equivalent, same ideas with starting shells. At most, there's something which starts up these separate tasks. For example, if you're doing any form of web server, a very common package for doing that's one called Cowboy, which handles the connections for you. And it's every time you get a connection, it starts up a new process for doing the connection. And then you do your stuff with that process. But there's no central thread of execution as such. Yeah. Yeah. Okay, so why is Erlang interesting outside the telecoms world? I mean, we were trying to solve trying to make it good for systems of this type of problem domain. So lightweight, the concurrency, the fault tolerance, the timing constraints. This is, for example, where you yes, lost stuff for it, continuous operation. Well, the thing is, of course, that's not just telecom, right? Basically, any web service has all these requirements. At least if you start asking them. Yeah, of course I want to do lots of things at the same time. I want lots of customers. I want them to come in at the same time, not wait the system. Yes, it should not crash, or rather, no, it should not crash. It should keep going as long as possible. Otherwise, I'll lose my customers. I will have timing constraints. Things have to happen at a certain time, and the system should not block while it's doing other things like this for it. It should be continuous operation. So all these are very common things you want for a lot of services, a lot of different types of systems. That's why Erlang has become interesting, or is interesting for these type of things. And that's something we did by mistake. Mistake. We weren't out to solve the general problem. We were out to solve our specific problem. And what we found was that problem is much more general than we imagined. Right? So I was honestly very surprised when someone started implementing yours, which is a web interface package on top of Erlang, one of the classic ones. I said, why would anyone use Erlang to do web services? Right? I don't know. I must do web services. I was programming telecoms. But it just works. Right? And that's why it's become used a lot, mainly outside telecoms. I think it's not much telecoms left in Erlang. We use for everything else, but not that. So I can boast a bit now. Erlang's one of those languages you actually come into contact with an awful lot, but you never see it.
It's probably 10% of our turnover, I would guess.
Telecoms, yeah.
As compared to 100% in the first 5 years of our existence.
Yeah, so we don't do much. We do a lot of stuff, but not much.
It's not that telecoms has shrunk, it's grown, but it's just...
Everything else is growing more. Yeah. And you'll find Erlang's everywhere, but you just don't see it. Right? Of course, the telecoms, if you're passing mobile data from your mobile phone, you're going through base stations with parts of it written in Erlang. At least the Ericsson parts of the Ericsson mobile base stations are written in Erlang. And Ericsson has about a 30 or 40% world market of that. So the chances are you're sending your data through Erlang systems, or systems run by Erlang. A lot of other things as well. Well, WhatsApp, of course, but anything, you'll find a lot of everywhere. You just don't see it, which is a bit unfortunate, actually, but never mind. Yeah, so that's why. That's why it is so good, because a lot of other systems have these requirements. I think why it's taken so long time for Erlang to get used a lot, this is, by the way, this is my purely personal view, is a lot of people, when they're designing systems, they don't always realize that they actually have these requirements. So the classic case, you sort of ask, what do they need? We need throughput. Yeah, we need a lot of throughput in our system. But you want to handle lots of things at the same time. Yes, of course we have to handle lots of things at the same time, but we need throughput. And the same thing with the timing. Yes, we want low latency, but we need throughput. And after a while, you find out you want these things. You don't want your customers sitting waiting around for a long time, because then they'll go somewhere else. Right? Not surprisingly. So yeah. And I can just say the Erlang concurrency model scales. When you start looking for it, it does scale. This having lots of small light processes communicating by sending messages scales, right? Much more than doing other things. Much more than, for example, sharing. The worst thing you can do is share immutable data. Sharing mutable state, that will kill you eventually. It can be done. The issue is not whether you can do it or you can't do it, but how good is it and how well does it scale and how much effort you have to put in to make it work, right? And so you can do it, yes, but it's a lot of effort. So that's the Erlang side of it. So, by the way, any questions on anything? So that's the concurrency and the error handling bits. And yes, we tried to keep it simple, and yes, we did manage to keep it simple. And yes, those principles actually suffice to build these things, which I sort of with hindsight I find very, very surprising, to be honest, that it does actually work. So now we'll look at the language side, and for that we will use LFE. That's the LFE mug. I've got a few stickers with me. We're running out of stickers. I don't do the stickers, by the way. Yeah, so LFE. So what is it? What isn't it, to start off with, right? It's not an implementation of Scheme. It's not an implementation of Common Lisp, and it's not an implementation of Closure. Okay. Because there are properties of the Erlang virtual machine that don't allow you to do this efficiently. You can do it, but not efficiently. So that it isn't that, right? But it's a proper Lisp. What is it? It's a proper Lisp in the sense that it's a complete set of Lisp. It's a Lisp. It's just a different Lisp with a lot of features, and it uses the properties and the limitations of the Erlang virtual machine. It's based around that. So in that sense, it's in a similar situation as to Erlang. And it coexists quite happily with Erlang and OTP. So if you want to write parts of your system in LFE and run it with other parts in Erlang, fine, it works completely. It it integrates perfectly with the OTP system, so you can just base it on top of that. And it runs on the standard Erlang virtual machine. So you don't need a special virtual machine to run or anything like this for it. It just works. So, yeah. So, how many people know Lisp? How many Lispers here? There are a couple. Okay, a couple. Okay. It's a hard life. So a little bit about why Lisp, the goal, well, the properties of the Outbeam and the LFE, and if you have time and if you're interested, we can talk a bit about implementation as well. So why Lisp, right? And yeah, question. Do we actually want to write stuff that looks like that? That is old version Lisp 1.5 from about the 60s, I think it was. 50s, 60s looked like this. Right? And if you try to start to decipher that, you'll find it's actually implementing three set functions. There's a member function here, there's a union function, there's an intersection function here. That's what it does. It's actually quite logical once you get around it. And here we're just testing the intersection between these two sets and the union of those two sets. That's what it's doing. That's old Lisp, right? This is what the equivalent ones look like in LFE. If it's better or not, that depends how you view it, but it's exactly the same type of code. So here's a union. So if we're trying to using lists as sets, if we're trying to do the union of an empty list and a set, we just return the set. Otherwise, if it's a head and a tail, here we just check if head's already a member of the set, we just call ourselves union on the rest of the list. Otherwise, we put the head back into the new union we're creating. It's very straightforward when you look at it. Honestly, it is. Truly, it is. Trust me. But why Lisp? I mean, okay, Lisp is actually, in one sense, a very easy language, a very simple language. So it's got numbers. Nothing strange here. It's got numbers. 1, 5.6, and 9, they're just numbers. It's got symbols. So these things, which in other languages might be variables or something like this, are actually things in Lisp. They're symbols. They have properties. They have a name. They know their name. They can have values and other things that are connected to them, right? So they exist as such. So the do is a symbol. It's a thing, right? It's an atom or symbol. We have lists. We have got, here's a list 1, 2, 3. That's nice. We've got a list of the symbols A, B, and C. So we just write them down, parentheses. We can have lists inside lists. So this is a list of elements where the third element is, again, a list. We can build up lists like this. We can, another list. That's a perfectly decent list, but just, it's got the symbol greater than, the size, and 4 here, right? And we can make another list. This is a list if, right? If this, then we'll have this list here and bump and drop it down. That's starting to look interesting, right? And we can go another step up here. We can make another list here. This is the list with the fun, the test, the list of size. We've got this thing at the bottom of it. And the interesting thing here, this is actually code. Right? This is code. That's a definition of a function, actually a definition of a function called test of one argument, which tests if its argument is greater than 4, and then it calls the function bump it, otherwise it calls the function drop it. But it's a list. It's pure data structure. That's one of the things that makes Lisp so interesting, is because the code is just straight data structures. It's extremely easy to work with it, to do code, to process code, to look at code, to generate code, to write macros, compared to almost every other language. So it's homoiconic. And, well, it's come a lot since 58 when the original one came. It's come quite a long way. There's an awful lot of things being done in Lisp. It's a programmable programming language. Because I've got this thing with a code, and the code is just data, it's very easy to generate code as data. I just build a data structure and it just happens to be code and I can run it, for example. It's good for exploratory programming. The near syntax list, I don't know, some people say it's a very simple syntax and some people say Lisp doesn't have a syntax. It's just a list, right? Depending on how you view it. But it is a very simple syntax. And there's quite an awful lot of things being done in it. So it's a very nice language. Don't be scared, if you haven't programmed Lisp, don't be scared off by the parentheses. Truly. There've come another number of alternatives where they tried to rewrite Lisp looking at more Algol-like syntax. There was one in the 80s called R-Lisp, which tried to look Algol-like, right? But it's still the same basic structures underneath. It just didn't quite work. But don't be scared off by it. It's extremely simple syntax. It's very simple to use. So that's why Lisp, right? So the goal of LFE was to make it a proper Lisp. I wanted something that actually was something, not just a test, not just an experiment for it. I wanted to work efficiently on the beam, which is the name of the Erlang virtual machine. So there would be no reason not to use LFE for efficiency. It's just as fast as Erlang, as fast as anything else on the beam. And I wanted to interact seamlessly with the Erlang OTP. So I just plug my stuff into the standard Erlang stuff and use all the OTP libraries and write things with it. So if you want to write a behavior in Erlang, fine. If you want to write an LFE, fine. They work, or everything works. That was the goals. Yeah, new skins from. If you haven't heard that CD, it's fantastic. Okay, so it's like plug for it there. It's a very good CD. The thing is, so how does this work? Well, we've got the Erlang system, we've got the Erlang virtual machine, the languages, all the OTP libraries, and what we do is we put LFE in its libraries as a skin on top of it, which allows us to put things in, change things and add things we want, but we've got access to all these things as well for it. So we use all of OTP, of course. It's there. It'd be stupid to rewrite it. It's an awful lot of code there. It'd be stupid to rewrite it. Yeah, I forgot to say one thing about OTP. I mean, OTP was started to develop it. Well, the ideas came from about 90. The basic ideas behind OTP and how you build these systems, they're from the beginning. But the actual OTP system was starting to develop around 95, I think it was. That's what became, R1, I think, came in 96 or something like this, the first version of it. So a lot of these, it's been around a long time, and there are very few bugs in it, to be serious. If you go onto the mailing list, they complain about 1 or 2 packages with bugs in, and the rest no one says anything about. That just works. So there's a very good reason to do this, to do it this way. And if you looked at Elixir, for example, they do exactly the same thing. They take the whole OTP system, they put a skin on top of it. They have a different skin, but exactly the same idea. They're using everything that's there. So yeah, so the sequential, so I didn't say much about the sequential language on top, the Erlang sequential language before, but it has a number of properties that affect any any language you want to implement on top of it. So for example, it has immutable data. It just has, right? There is no way around that. You cannot implement mutable data on the system at all. If you try to go in a low level and hack it, you might be able to do it, but the chances are you'd either crash things or make it behave very strangely. It just doesn't support it. We only have a predefined set of data types. There are no user-defined data types at all. That's it. This has to do with the code handling. Because the system is very dynamic, you cannot define things over a whole system because the system concept just doesn't exist. We have support for pattern matching built into the machine. And it's support for functional language and the way it handles modules and code. And there is no global data in the system at all. We don't do global. We don't do sharing and we don't do global. That's it, man. Forget it. Yeah, so I'll just talk some of the things around this. The syntax, from a Lisp point of view, it's a pretty standard-like Lisp syntax. It's a bit of scheme influence and quite a lot of common Lisp influence. So I've got the parentheses, I can use square brackets if I want to. The symbols are like same syntax for symbols as for common Lisp. I've got separators. I've got tuple constants, binary constants. I'll talk a bit more about those later. It does do one Lispy thing, or Erlang-y thing here, that strings are lists of code points. So a string is a list of numbers in integers. This is not uncommon in functional languages. It can cause a bit of confusion sometimes, but otherwise. We've got character constants and stuff like this. This is just pretty straightforward, actually, the syntax. For a Lisper. Sorry. Data types. Again, this is forced on us or given to us by the machine. It only has a fixed number of data types. That's it. I cannot define my own data type. I can fake it. There are a number of alternatives to that, but I cannot do it, seriously do it. We've got numbers, we've got atoms, they're Lisp symbols, we've got lists, tuples, which are Lisp vectors. We've got the Erlang maps, the binaries, and a few other opaque types, for example, process references and stuff like this. So a few things here with atoms and symbols. If you're coming from Common Lisp, which has a package system for handling its symbols, Erlang cannot do that because we only have one namespace for all atoms. We use atoms for symbols. We just have one namespace, so we cannot do Common Lisp packages. Right? There's just no way around that. You could try faking it by if you've got the package bar with the symbol foo, you could translate that to bar : foo, but that would really screw things up if you tried to do that. Honestly, we just don't do it. So that we can't do Common Lisp packages. Forget it. Yeah, I'm not going to talk numbers and numbers. That's fine. We've got big nums for integers and 64-bit IEEE floating points with all their strangeness in it as well. We've got the one. I like binaries. I like binaries actually. So what's a binary? Well, it's a byte array, okay, which is not very exciting, to be honest. Okay, but you can access it very nicely. So this here is a form. Lisp form, which creates a binary of 3 bytes containing 1, 2, 3. Okay. This form is a binary which contains, well, it contains a 16-bit little endian field containing the value of t. It contains a 4-bit field containing the value of u, a 4-bit for v. It contains a 32-bit field containing a floating field containing f, and b here is a bit string. So I can write down exactly what I want the binary to look like. I don't build it, I describe it, and the system will build that for me. So if I've got values in the variables t, u, v, f, and b here, I write down that structure, and the system will build that binary for me. Okay, which is very nice. It's very functional, very nice, very declarative. I just say what I want it to look like. I don't build it myself. And even that little bit's quite a lot of code if you do it in C. But yeah, so I've got types, I've got size, I've got endiness. I can have little endian or big endian. I've got signs, I can have signed runs, signed numbers, and things like this in there as well too. So that's okay. But here's a better example. That binary builds an IP version 4 packet. That describes and builds one. So there's a 4-bit version. There's a 4-bit header length. There's an 8-bit service type. There's a 16-bit total length. There's a 16-bit ID. There's a 3-bit flag field here. There's a fragment offset, 13 bits, etc., etc. So if you go into Wikipedia or anywhere and look at the description of an IP packet, that's what it looks like. And I can just write it down like this. And if I put these things in, I build it, the system will build it for me. The interesting thing is also, when we're looking at pattern matching, if I use that as a pattern, I can pull apart an IP packet and extract all the fields in one go by just writing down the binary that does, or writing down the pattern that does that, which looks exactly the same. So this is when binaries get interesting. So they're very useful for doing protocols. I don't have to build it, I write down what it looks like, and the system builds it for me. So they're very nice. It takes away awful lot of problems doing these type of things. And they work, which is even better. So they're binaries. We've got records. Erlang has a concept of a record. So we don't have user-defined data types. So how can I get, one way of getting around this is we use tuples and we put a tag at the front of the tuple and says what this is. Right? So here's an example of a tuple here with a tag person saying this is sort of a person type information. And it's me, my age, yes, and a list of things I'm interested in. This is just a person record saying that, right? And this is a way of getting around not having user-defined data types. This is one standard way of doing that. I use tuples and I have a tag at the beginning saying what it is. Of course, someone else could use the tag person to mean something completely different. Tough. That's the problem with it. But of course, we've got support here. We've got a def record macro where I can define a record, the name with all the field definitions and so on. And when I run that macro, it generates a large set of macros for me for accessing that record. So I've got a make macro here. I've got a test. I've got a pattern here macro which generates a pattern for matching against that record. I've got accessor records for all the fields. So I can extract the field or set the field and do things for it. So this is just a very Lispy interface into that. So I have one macro which generates a sequence of other macros. This is typically how you do things in Lisp. So yeah, I've got a support directory for records. If you want to make any other data type format, predefines formats for data structures, you can do exactly the same thing. There's nothing strange. Yeah, modules. We talked a bit about modules, a little bit more about them here. They're very basic. If you're coming from an object-oriented world, don't think of them as classes. Classes have a much more inherent meaning than an Erlang and LFE module. It has a name, it's got a bunch of functions, and some of the functions are exported so they're visible on the outside. That's it. That's all the module is. There are no module variables, there's no module data, there's no module anything, they're just functions. Yep.
So can you write a module in C?
The problem, yes and no. Okay, yes, you can do that, but the problem is getting it into the Erlang system so the Erlang system recognizes that as a module.
So you have to implement the messages and all this stuff.
Modules and processes aren't the same thing. Modules is just code.
So a process you can write easily in C?
You could write yes, you can write a C process, a process in C. I'm not saying it's easy because it has to interact with the rest of the system, but yes, you can do that. There is support for doing that actually. Or another easy way is use an Erlang port and have the external thing as another operating system process which you communicate with.
So each process is an operating system process typically, or is it
No. So when you start up Erlang, you get one operating system process. So all the Erlang processes are implemented internally inside by the virtual machine. There's a bytecode. There's an emulator. There's a virtual machine in there.
There's a virtual machine.
Yeah. But what your processes are, if you get the communication right, get it right, you can write a process in C. If you want to do that, run it inside the Erlang system. You tend to avoid doing that.
But crash
Pardon?
You're not running native instructions, you're actually running emulated stuff.
The Erlang, yes. You're running emulated. That's why you get the crash safety. If you write a process in C, you've got no safety nets. Segment-wide relation will take down the whole Erlang system. Well, you have a choice. You can write in C and make it go faster, or you can write in Erlang and make it be safer. Take your pick, right? But yeah, it's a flat module space. Again, there are no special modules, they're just modules. As I said, it's a very egalitarian system. And as I said before, modules, code handling. We only have functions. Functions only exist in modules, and the only thing you have in modules are functions. And as I said before, there are no interdependencies between modules. Yeah. So how do we define a module? We have a def module. This defines the module arith, and we're going to export the functions add of 2 arguments, add of 3 arguments, and sub of two arguments here. This defines the module. And down here we define the functions. Now it starts to get strange. Well, if we look at sub first, it's sub of AB just returns minus AB. That's what that does. But I've got 2 adds. I've got an add of AB which returns plus AB, and I've got an add of ABC which returns plus ABC. So what's going on here? Okay. So, a couple of things. Erlang functions cannot, I'm saying Erlang here, but this applies directly to LFE as well because we're running on top of it as close as we can. You cannot have functions with variable number of arguments, period. You can't do that. But I can have functions with the same name and different number of arguments, and they're different functions. So here I've got an AB add of 2 arguments, and here I've got an add of 3 arguments, and they're 2 separate functions. And if I call add with 2 arguments, I'll get this one. If I call add with 3 arguments, I'll get that one. If I call add with 4 arguments, I'll get a crash because there is no add of 4 arguments. So you cannot have variable number of arguments. The system just does not support it. You can build something on top which does it. For example, everything can have one argument, which is a list of arguments, but then you won't get proper native support in it. That's just a property of the system. The number of arguments we just call the arity. So here you've got an add of arity 2, and here you've got an add of arity 3. That just goes through everything. It's very practical sometimes. For example, typically you have a start function of 1 argument, which calls a start function of 2 arguments with some default arguments, or sometimes called bigger ones too. It's very common. But it's just a property of the system. That's why, for example, I'm saying here I'm exporting add of 2 arguments and add of 3 arguments, because they're 2 separate functions. Just one. And that's not going to change. It's too baked in. Yeah, so LFE modules have got declarations. That's the thing at the top here. I can put other declarations in here as well. It's function definitions. I can define macros, and I can actually define functions that are evaluated at compile time as well too, which aren't exported afterwards. And I can define macros anywhere in the code, but they have to be defined before being used. There's nothing strange about that, really. Yeah, Lisp 1 versus Lisp 2. If you're not a Lisper, this might be slightly strange. There are 2 large different schools or families, you might say, of Lisps here. And that is how symbols are evaluated in the function position and the argument position. How are you going to do that, right? So if I've got this expression here, foo 42 bar, this is actually in Lisp sense, this is calling the function foo with a 42 and the value of the symbol bar. The variable bar here. That's what that syntax means. Right? And in Lisp 1s, I'm getting the function definition here and the value here in the same way. These just have a value. And if I use in the function definition, I'll get the value and try and call it as a function. If I have it in the argument position here, I'll just get the value and pass it into the function. So this is very nice, it's very clean. That's why the Lisp 1s, there's only one of them, only one value for it. Actually, they all have others, so it should be about Lisp 4 or Lisp 5, but from this point of view, there's only one here. Lisp 2s have 2 things connected to the symbol. So here, I use the function field of it to get the function, because it's a function, it's in the function position. I'll call that function, and here I will use the value. So each symbol has a function field and a value field. So I could do foo 42 foo here, and here I'll be using the function definition, and here I'll be, or the function value, and here I'll be using the value for it. So there are two schools. And the original Lisp were Lisp 2s. Lisp 1s are cleaner, they're nicer. But if you're going into Common Lisp, it's a Lisp 2. You have this feature for it. And so yeah, what do I choose? I have to choose one of them, right? And originally I actually did choose Lisp 1. I was looking at Scheme, two very common Lisps. Scheme is Lisp 1 and Common Lisp is Lisp 2. Okay. So we're going to Scheme, so it went Lisp 1. Right? So I could write a function, I could define foo here of 2 arguments and 3 arguments, I could define bar, and I could just define baz as a variable here with a value, a lambda here, and I could call baz, and I could call foo, and I could call foo there. That's great, worked. But I felt that was inconsistent and unfair. Because if I've got a global function foo here, I can have multiple functions with the same name of different arguments, different arities. But here I can't. I can't have a baz with one lambda. If I redefine baz, I can only have one definition of baz in here, right? Which has one set of arguments. So if I call this with the wrong argument, I'll get an error here, right? And I just felt it was inconsistent. Consistency is nice, because then you understand better what's going on. Things are consistent. So we went to Lisp 2. So I can have foo up here of 2 arguments and foo of 3, and I can have a baz of 1 argument and a baz of 3 here, because I define them through an f-let here, which just says this is defining functions. So I can do this. It's consistent. Which is nice, but it's not quite the same as a lot of other things. Yeah. So that's why I felt it just fits better into how it works everywhere. Just make it more consistent. Actually, it's more. I call Lisp 2 plus because I can not only have 2 of them, I can have multiple, as many of them as I want. Right? I can have many bazes as I want there, all different arguments for it. So that's that. We do pattern matching, yes, of course. We could support the machine for pattern matching. We use pattern matching everywhere. And if you haven't used pattern matching, you're really missing out on something. Truly. Once you get into pattern matching and understand it and use it, you will sort of wonder, how could I not have had it pattern matching? So yeah, the Erlang virtual machine supports it. We support it directly as well too. In function definitions, in let's case receives, in macros, other things. We support pattern matching everywhere we can, right? So again, we have the let construct. Normally Lisp, which binds variables, we have patterns in there, so you can match against what things come out and bind variables and pull things apart. We've got a case which takes an expression and then uses pattern matching to choose the clause. We get a lot of these things for it. The receive, that's what extracts, how a process extracts messages from its message queue. So when it gets sent a message, the message is put in the message queue, and it does a receive when it wants to extract a message. And it uses pattern matching to extract the messages. So I can say, give me a message that looks like this. It'll take the first one there. If none there, it will just sit and wait until one arrives. So we use pattern matching there as well, too. This is how you bind variables, through pattern matching. We do everything with pattern matching. We can define a function with separate, we call them clauses, where you've got the arguments here, which are patterns now. The argument list is now a list of patterns, and we can use pattern matching to select which one we want to do. The Lisp con we've extended with a pattern matching clause there as well. So I can define the Ackermann function like this. So it takes 2 arguments, and we're using patterns here, and it says if this is the first argument, I'll do this. I'll return plus n1. And if the first argument is not 0, but the second argument is 0, then I'll call Ackermann with these arguments. And if neither of them are 0, I'll call Ackermann with these ones. There's just a different way of expressing it using patterns. These are quite easy, but you can get quite far. So here we have the member function, which tests if an element is a member of a list. And the traditional Lisp way of writing this is with a con, and I say, is this the empty list? Then I'll return false because I couldn't find it. And is the element I'm looking for the first element of the list, which is what car means here, then I'll return true. And if it's not the first element, then I'll call myself recursively on the rest of the list. So basically stepping down the list, checking every element. Is this the one I want? Is this the one I want? If I found it, I'll return true. If I get to the end, I'll return false. I can write this using pattern matching. So here I'm saying we have an X here, and we have a list, So I'm using the same syntax for constructing as a pattern, and I say, is X the first element of the list, which is what this test is, then I'll return true. If it isn't, I'll call myself recursively on the rest of the list, and if the list is the empty list here, I haven't found it. So just a different way of writing as patterns. These don't really show the full power of patterns. Yeah.
In the last example, the first pattern, would you be able to replace E with X in the
No. I made the choice not to do that.
Okay.
What you find in Erlang with pattern matching, that if a variable occurs more than once, there's an implicit equality check. So there I could write X here, and there'd be an implicit check that they're actually the same here. Actually, it'd be this test exactly the same. I decided not to do that. It's a bit more verbose, but it's actually cleaner. Do it this way. So yeah. For example, I could write a function where I'm matching against IP packets, and I could use my the binary thing I read before, as the pattern to match against it and pull things apart in one go, which is about the most complex pattern I think I've seen. So yeah, pattern matching is wonderful. We've got macros, of course. They're unhygienic in that things can escape from them. But seeing all variables as scoped is not as bad as it could be. Okay. The problem is we don't have a gensim. Okay, what gensim does, it creates a unique symbol, guaranteed not to be like any other symbol. Okay. We can't do that. The Erlang virtual machine just does not support that. We can't do it. Yes, I can generate a symbol, and I can generate a symbol with a funny name, but there's no guarantee that it's unique. Someone else could get the same funny name and will suddenly have the same symbol. It's just a property of the machine. I can't do that. There's also another feature of the Erlang machine, that when you create a symbol, create an atom, that's put into an atom table, and it never goes away. And when the atom table fills, the machine crashes. So you don't want to do things like generating atoms on the fly. So you can't do it. You can try, but it doesn't work. It's generally not a problem. At the moment, they're only compile time. So you define them inside a module, and they're used by the compiler. But I'm working on being able to export them at the moment. And there's, well, a set of core forms. They're the basic things. I can never shadow those with a macro. So I've got the cons form, which builds a list. I cannot define my own macro called cons to replace it. I can't define a function called cons either, for that matter. Well, I can define the macro, but it'll be ignored. It's just a little bit of self-preservation, right? So yeah, I can define a macro, add them here, which takes 2 arguments, returns a form plus AB. This is something called the backquote macro, which does quoting and expanding at the same in one package, and says, yes, this build a list with a plus here and the value of A and the value of B. This just expands to that. I can do a macro here of average, called average with args, which is the whole list of everything I pass into it, which will return a form which calculates the average of all the arguments, numbers I gave in the call to it. And it will do the length, evaluate the length that, because it knows the number of arguments, so evaluate the length at compile time, but just has to plus all these in runtime. I've got a list star here, which creates a list except for the last element which is appended to it, but I can define all these as macros. So yeah, macros can have any number of arguments. They get one argument, which is a list of all the arguments, and can have multiple clauses. And yeah, we have, coming from the list, yes, we have the backquote macro, which is very nice, which allows me to write things down as I want them to, what I want them to look like, and the system will generate code to build that structure or match against that structure, which is what I'm doing up here. Yeah, this is a very nice little bit of code example. It's real code in the sense that it actually works, but it's not real code in the sense of part of a product. So as I said, we had in the lab, we had our test system, and we wrote a library on top of this so we could run this, we could access this through Erlang, of course, which means you can access through LFE. And then you could make phones ring, and you could lift a receiver, and things could happen on a little exchange. Or if you didn't have the hardware, you could run it with a virtual so you could see graphics, so you could see the thing for it. That still exists, by the way. I think we would have found that, the graphical interface for it. So these two functions these are run in separate processes. What happens here, when we're now in the state, we've lifted the receiver, we've dialed the number, and the phone is ringing. So we're in the ringing state, right? And the A side here, that's the side that's made the call. And the B side is where the phone's ringing. So here we hear a dial tone in our receiver, and here the phone is ringing. Now we implement this, we have two processes, one on the A side and one on the B side, and they're talking with each other, of course. There are actually more processes going on, but the logic we split, even in this very simple case, splitting the logic up into two separate processes makes things much easier. If you're careful, if you're asynchronous. So what can happen here? Well, the A side, I can give up, and I can put the receiver down, which means I'll be sent an on-hook message. So the system sends me a message. As I said, we're reactive. The system sends me a message, an on-hook message, when I put the receiver down. So I send, this is the send thingy here, I send across to the B side cleared. And then I just stop, I call the teleOS here to stop the tone, this turns, and then I just go to the idle state by calling the idle state function. Address, that's my address. That can happen. So what can happen on the B side? Well, the B side can get it cleared, which means that the A side is hung up. And what does it do? Well, it stops the ringtone, and it just goes to the idle state. So these two processes working together. The other thing that can happen, of course, is the B side can lift the receiver, which means the B side process here is now going to get an off-hook message. And what do? Well, we tell the A side we got answered, and then we go to the speech. Go to the speech state here for it. Now the B side, well, the A side is going to get an answered, and it's going to stop the tone, and it's going to tell the switch to connect these two things together. And it's sort of convention that's the A side that does the connections with the switch. And then it goes to the speech state by calling the speech function. What can all happen in both cases is this is someone trying to call us. Okay, this is what the seize is. This process is trying to call us. And of course we have to reply rejected because we're busy, so we have to reject it, which is what we do here, and we stay in the same ringing here. And this just says we're going to ignore any other message that arrives. We're just going to throw it away. So I have these two processes. They're communicating with the outside world through messages. The teleOS actually sends messages to the switch saying, connect these things together, remove this down, take it down, etc., and so on. So everything works through messages here. And all these messages are asynchronous. And if you tried to put synchronous communication in this, then you couldn't handle the receive because they're sitting waiting for something from the other end. Right? The whole thing works, it's very simple because it works, everything's asynchronous. Do you have a, okay, sorry. This is a very simple example. And this is very Erlang, very Lispy code. One, we have tail call optimization here. This is the type of code we're doing from the very beginning. This is our view of the world from the very beginning, so we had tail call optimizations from the very beginning. And this is just very much how it's done. Everything's asynchronous. Yes, I can get an on-hook and I can get an off-hook at the same time. So I'm going to send a cleared across, and this one's going to send an answered at the same time to me, which means I will get the cleared when I'm in the speech state, and here I'll get the answer when I'm in the speech state. So speech state has to be able to handle this. Just saying, well, it can ignore it or throw it away or do whatever it wants with it, but it has to handle it. I don't have the synchronization problems. Well, I have a different set of synchronization problems. And that means this never blocks. I can always be sent to seize. Whatever state I'm in, I can always be sent to seize, and I'll always reply immediately, I'm rejected. Except, of course, if I'm in the idle state, but then I'll do that. That's very sort of classic type Erlang code for it. And yeah, this works. You run that through the compiler, and it'll say yes, it works. Yeah, why? Okay, why? It's a bit weird, yeah. It's a bit strange. No, it's not. Erlang syntax, if you look at it, it looks strange. But then again, all functional languages have strange syntax. You cannot find a functional language that doesn't look strange, right? Even F#, which is supported in the whole system, the syntax does not look like C#. But the only thing that's the same is the sharp, right? So that doesn't worry me. The Erlang syntax, however, is actually very simple. It's very simple, it's very consistent. when you actually start looking at it. It's one thing people complain about, well, a number of things people complain about Erlang, and one of the things is that the syntax does not look like JAVA, right? It does brackets the wrong way, it doesn't use semicolons as the world should, etc., etc., etc. But if you compare it to that syntax, you'll actually find the Erlang is much simpler. The Erlang syntax is much simpler than most other programming languages, except perhaps Lisp, which doesn't have a syntax. It is. It's simpler than almost anything else. So why? Why? Well, I like Lisp. I learnt Lisp before I started working with Erlang. Lisp was probably my first proper high-level language after Fortran and Pascal. I like Erlang. I like the Erlang system. I think the Erlang system is a very nice way of attacking a big set of problems in the world for it. And I like to implement languages. Okay, that's fun. Implementing languages is fun. So, of course, doing LFE was natural, right? Best of all three worlds in that sense, so doing that for it. And it's actually grown quite a lot since those days for it. So, yeah, that's me. That's Erlang Solutions me. And that's private me, depending who why. And here are a number of links into the various LFE sites. So there's an LFE.io page there. I have not the one who's done that. It's a very good looking page, but that's not my work. It's from another guy called Duncan McGregor who's done that, who's very enthusiastic Lisp. He's the one who's done the t-shirts, by the way. It's an LFE t-shirt, the standard LFE t-shirt. This is where you'll find my implementation. You'll find under the LFE site, there's more things, packages coming, work being done there, the documentation and stuff for it. There's the mailing list is a Google group, if you're interested in doing that. There's an Erlang Lisp IRC under Freenet, if you want to do that as well too. So that's the interface for it. And yeah, I think that's about it. Yeah?
Yeah. Question, can you give us indication about performance?
It's the same as Erlang.
Same as
Yeah. Okay. That was one of the goals, to make sure. That's why if you look at the skin, the LFE skin's quite thin. That's why most of what I've said here about LFE, you can just change the syntax and you're talking Erlang, right? Because that was designed decision to keep the skin very thin. That means it's inherited a lot of Erlang good stuff, but some of the Erlang bad stuff as well. And while some complaints are Erlang completely up the wall, some of them are quite true. Right, so you just have to pick your ones. But yeah. So yes, that was a goal to make sure it wouldn't go slower. And as it interacts completely with it, the whole thing. Any? No? Completely silenced? Yeah.
I have two questions.
Yeah.
I don't know if anyone knows.
Well, I had another question here, but take one.
But they have more to do with Erlang proper than the LFE.
Yeah.
So I don't know much about Erlang. I haven't used it, but I looked at a few code samples. And it did look a lot like Prolog.
Okay.
It seems to borrow a few concepts from Prolog. So was that a goal?
No. The original Erlang system was done on top of Prolog. So what happened, Joe had written down a number of telecoms rules, and someone came by and said, that looks like Prolog. And he was actually been planning to implement it on a Smalltalk machine, but it took a long time to get the Smalltalk machine, so he started doing it in Prolog instead. That's where it all started. So it started as a Prolog interpreter, and originally it was just Prolog rules. If you go back to the really old stuff, Joe found an old version, 1.03 or something like this. It's Prolog. So some of the syntax is Prolog inspired, like the fact that Erlang variables start with an uppercase letter. That's Prolog, and some of the syntax. But the semantics is completely different. So there's no Prolog semantics. One of the things we did when we developed Erlang was we moved away from Prolog because we didn't want some of the semantics. That's why it became functional instead of logic. Yeah. And
So how do you guarantee responsiveness in the presence of garbage collection?
how do I guarantee?
Guarantee the responsiveness of the system about garbage collection.
Okay. So there are a couple of levels. One is there's a preemptive scheduler. So every time, literally after 2,000 function calls, the process is running is rescheduled. So you can have a process that's continually running and it will never block the system. Again, think operating systems. You can do this in operating system as well. You can have a process that's continually running in the operating system and will not block it. It will slow it down, yes, but it won't block it. It's the same thing in the Erlang system as well. There's a preemptive scheduler which makes sure that no process will ever block the system. Yes, that costs to do that, of course. But again, that's something we're willing to do. We had to do to make sure the system had low latency, reactive.
It's not a real-time system.
We call it soft real-time. Hard real-time, people say, is not real-time. We say soft real-time, and you have timing constraints, and most of the time they'll be fulfilled. Occasionally they won't be, but for this type of application, you can accept it coming a bit late sometimes.
So what did you design it for in practice when you talked about that?
Telecoms applications.
Oh, is it a millisecond, or is what is the resolution? If you want
Aha, okay, milliseconds. Milliseconds.
Milliseconds of reasonable time. So I'll give all within a millisecond if I specify that.
Yeah, we'll do that. Okay, then that was a very short time. Now it's a very long time. Probably today would have had microseconds or something like this with today's machines, but millisecond was a long time. The other thing with garbage collection, so yeah, the system of course can't stop and garbage collect. You can't sit there for 5-10 seconds while everything's down and it's garbage collecting. You can't do that. The way we solved that problem was that each process has its own small heap. And when you garbage collect one process. And because process heaps are small, the garbage collection time is so short, it's acceptable. That means, for example, that also means the effect of that is when you're sending messages, you're copying messages from one process to another. Okay. Which sounds really bad, but it isn't. Not just for garbage collection things. But so I did a number of experiments with the real-time collectors.
So each process has the same memory footprint size?
Nope, it's dynamic. It varies.
But then you can have fragmentation of it.
Yeah. Well, each process heap won't be fragmented because it'll be allocated as one block.
Yeah, but then if you have like millions of processes, then
Yeah. Yeah. But each process won't be. But you can't get around that anyway. I mean, if you're going to have millions of processes with that much data, you're going to get fragmentation however you do it. If you do a shared heap, yes, you're going to get fragments because data is going to be spread out all over it anyway. If you have a shared heap, then you have to do a real-time collector, which itself is very interesting. It's fun. But it's an interesting problem, especially if you're going multi-threaded. Then it gets really difficult.
So has it ever been a problem?
Pardon?
Has it ever been a problem in practice, like in the telecom?
No.
Fragmentation. Sorry, when you say
Fragmentation.
yeah, I've experienced it twice. So it's extremely rare because processes come and go, and as soon as you terminate the process, you free all the memory. So there's a lot of opportunity for optimizations. And those instances where we've seen fragmentation, it's been when the VM has been running for years on end with extremely high loads. But yeah, I think twice in my 20-year career we learned that.
Yeah, Francesco's been working with Erlang about 95?
94.
94, yeah. He's on the doing stuff side, right? I implement things. Yes, no, that is not a problem. So going multi-core or multi-threaded, which in this case is the same for Erlang's same, introduces a whole new set of problems. And memory management is one of them to do that efficiently. And actually, their copying is better than having a shared heap. Because if you have a shared heap, you need to do a real-time collector because it can't stop. Then you get into a problem with synchronization and locking the heap from the other threads that are doing work while your garbage collector thread is doing garbage collection. And the one thing you do not want to do if you're running multi-thread or multi-core is lock. That's about the worst thing you can do. Sometimes you have to do it, but it's the worst thing you can do. I mean, I've got a very simple case of an Erlang program which starts up about, 2,000, 3,000, 4,000 processes, as many as you want. And the more parallelism you've got, the slower it goes. They're being spread quite happily over all the threads, but it's just the locking kills it. Okay, it's pathological, but that's an example for it. So yeah, that's one benefit of doing copying, because I don't have to lock, or much less locking. I get better memory locality. I get better cache performance. It seems strange, to be honest, but it does do it. But you're copying data, yes. But getting back to the garbage collector, it means the garbage collection time for each process is small. I don't have to do things. I can just collect the whole process in one go. A lot of work is put into the machine to keep the latency down. They sort of come out and say, yeah, we've cut down the number of locks now. We've got fewer locks this time now. The last one I did was 18. The latest version was the timers. Now they have separate timers for each thread, which before they were sharing timers because it's more efficient. So yes. Okay, any questions on, yeah?
What kind of adoption does LFE take?
Adoption of LFE, not much, to be honest. It's getting there though. It's getting. If you look at if you look on Twitter, you'll see a number of tweets going up. No, sorry. Yeah, it's actually being used. A company's using it in a product. A small West Coast company. They're doing picture processing. They're not doing the picture processing in LFE, but managing that. They're doing that for it. I didn't know about that until I was told afterwards. We've done our system in it, so it's quite fun. It's spreading around, getting more use now. It's, I would say, production ready. There are no known bugs, I'll put it this way, in the system. Well, no one's reported a bug that haven't fixed for it. It's partially, well, the basic system is fixed. The basic LFE system is fixed, and people doing libraries and stuff like that on top of it as well. And also doing support for building releases. Now working with Rebar 3 to make suitable config packages for that and stuff like this as well. So it's usable.
One last question, if anybody has.
Okay.
Thank you, Robert.